For categorical variables, in Learning Outcome 19, we consider the situation where the variables had more than two categories, and we needed a new tool there, chi-squared, which gathered a total measurement of the variance between the various categories. Now we want to do something similar for numerical variables and consider multiple means. As usual, I'll rely on an example to set up the material. Today, I'll talk about baseball. Many sports have an obsession with their statistics, but I feel the importance of stats to baseball is particularly notable. So let's look at some baseball data. The dataset here consists of players from the 2018 Major League Baseball season and their performance in various categories. Here's just the start of the dataset, showing just a few players and a few pieces of data. What I want to focus on today is position and OBP, on base percentage. Position is grouped into three categories in this dataset: infield, outfield, and catcher. OBP is a measurement of how often the player makes it to at least first base when they are at bat. The question here: how much does the position category matter for OBP? Are infielders, outfielders, or catchers substantially better batters? Here's a summary of the specific pieces of data related to the research question. These are the three position categories: outfielder, infielder, and catcher. N is the count in each categories, and here are the means and standard deviations for the on-base percentage, OBP, for each category. There are three means here, since there are three categories. This differs from previous learning outcomes. This is not a single mean past a threshold or a comparison of two categories, such as treatment and control. New techniques are needed here. At a glance, it seems that catchers are a bit worse for OBP than either infielders or outfielders. There is a difference between the first two categories, but it is pretty small. Are these differences significant? This is what we want to know. The box plots give more information for the data in each category. We can see that even though the means differ, there is a lot of overlap inside the quartile ranges. So maybe even the larger mean difference between catchers and other players might not be significant. How do we figure this out? The hypothesis setup is the same as for the chi-squared situation. All the means in the actual population are equal. There is no variance. That's the null hypothesis. The alternative hypothesis simply says that there is some variance amongst the group, but it doesn't specify where the variance is. Two of these means could still be equal, but the third could differ. Maybe the outfielders and infielders have the same mean, but catchers actually show a difference. Like with chi-squared, this is just a binary choice. Is there variance in the population, or isn't there? Now we need to test this hypothesis. But what is the test statistic? What is the measurement of the variance in the sample? For chi-squared, the test statistic was a sum of expressions involving each count. N is the count of each category, and N null was the count of what that category would be under the null hypothesis. This was complicated enough. Here, the situation's even more complicated. We are comparing three different sets of numbers, one for each category. The data for outfielders, infielders, and catchers, for each group, is itself a data set with a distribution, with a mean, with a standard deviation, perhaps with outliers. What is particularly difficult here is that each group has variation within it, and then after this, I'm trying to measure variation between the groups. How do I measure this? The measure that statisticians have developed here is called an F statistic. The idea is that an F statistic is a fraction where the numerator is some measure of the variation between the groups, and the denominator is a measure of the variation within the groups. It needs to be structured this way to capture the whole situation. If the groups themselves, inside themselves, have very widely spread out data, well then this denominator will be large, and this makes sense since it's hard to measure the difference between the two groups when the groups themselves show a bunch of difference inside themselves. Likewise, if the groups have tightly controlled data all grouped together, well then comparing should be easier. And I can use box plots to express this idea. Here are three box plots. Relative to the range of values between them, these data sets have little variation inside each set. So I would expect a large F statistic here. But here are three other box plots that have exactly the same means as before. However, the data inside each category is much more widely spread, with much more overlap between the categories. even though the relationships between the means are the same here, so in one sense the difference between the categories is the same, since the categories are so widely spread with so much overlap, I should expect a much smaller F statistic. So that's the F statistic, a measure of variance between numerical data groups in categories. How do you actually calculate it? Turns out it's a giant mess and nearly impossible to do by hand. I could try to describe formulas for it, but they get unwieldy quickly, and there's not a lot of conceptual value in doing so for this course. If you want, just imagine a lot of nested sums in sigma notation with a lot of squared differences inside them. And if you don't want to imagine, then just be content to let R calculate the F statistic for you from the dataset. Well, how do we proceed then? Well, as with all probability models, there are conditions. And the conditions here are a bit more stringent than previous. And this may make some sense. There's a lot more heavy lifting going on in the mathematics behind the scene, so more conditions are required to make sure the probability theory works. Like with t-distributions, the categories need to be independent, no causal relationships between them. Second, each group needs to be at least somewhat normally distributed in itself. No strange bimodal distributions, no extreme outliers. And finally, the standard deviations in each group need to be somewhat similar. These conditions are satisfied by the example of the baseball statistics. I calculated the standard deviations earlier in the table, and they were in fact quite similar. The players are indeed independent. Whether a catcher is batting well doesn't really affect directly whether some other infielder is batting well. Finally, there is reasonable normality here. And this I haven't really demonstrated, but you could make histograms of each category and see a reasonable approximation of a normal distribution. There are outliers, which were shown on the box plots, but they're not too severe. All right, I have conditions. And as with all of the hypothesis testing, conditions met means that data randomly generated by the null hypothesis will make a predictable sampling distribution. And this sampling distribution can be used to get a p-value for our test statistic. The mathematics here produces something called an F distribution. It is the distribution of randomly generated F statistics under the assumption of the null hypothesis. Like chi-squared and t-distributions, it has degrees of freedom parameters. And now there are two such parameters. One is the number of groups minus one, and the other is the number of total cases minus the number of groups. What does this look like? Well, the F distributions look a lot like the distributions for chi-squared. And this makes sense. They are both measures of total variance among multiple categories. The variance is always positive. The null hypothesis says that there is no variance in the population, but a randomly generated sample will likely have, of course, random variance simply because it is a sample and doesn't perfectly fit the population. Therefore, the F distribution is large near zero. We expect most of the variance to be fairly low from the null hypothesis, and decays away. Again, showing that low F statistics, low variance is likely, but higher F statistics, higher variance is unlikely. I get an F statistic for my sample. Again, that's what R calculates, something I haven't told you how to calculate. Where that F statistic falls on this distribution determines its likeliness, and therefore its p-value for hypothesis testing. So now I can do the hypothesis test. I ask R to calculate the F statistic for me, and for the baseball data it returns 5.08. I calculate the degrees of freedom. There are three categories, so df1 is 3 minus 1 equals 2. There are 429 cases, so df2 is cases minus categories, 429 minus 3 equals 426. From this information, I can ask R to produce a p-value, and it returns 0.0066. As a percentile, this means that 99.33% of the possible randomly generated F statistics are below this value. Under the null hypothesis, there is only a 0.33% chance of producing the sample statistic of my data. With the usual thresholds of significance, I conclude that this is significant, and I reject the null hypothesis. What I am doing here is an analysis of variation, and this is abbreviated to ANOVA, which is the name for this statistical process. It's a new kind of statistic, the F statistic, and a new set of distributions, the F distributions. But otherwise, it is the same process. Generate a random sampling distribution, assuming the null hypothesis, look at the test statistic, find a p-value determining how likely the sample statistic was under the null hypothesis, and use the p-value to make a conclusion. For the baseball data, I've concluded that the sample gives evidence that there is some real difference between the on-bat percentages of outfielders, infielders, and catchers. I don't know exactly where those differences are. That's a question for a more advanced statistics course. But I do have evidence that variance exists in the population based on my sample.